In this video, we're going to cover the basics of group theory. So really like the minimal thing that we need to understand in order to comprehend regular group convolutional neural networks. So at its core, a group is really like a mathematical construct. It's just like vector spaces are. So that we have this formal definition of it. A group is a set of elements G equipped with a group product, and this is a binary operator that satisfies certain axioms. So what does it mean? So when we talk about the group, we talk about a set of elements from which we can take two of these group elements, and we can combine them together with the group product. So we multiply them together, and that spits out a new group element. That's this closure property. And well, it needs to satisfy certain other properties as well, which we'll go over in some examples. But importantly, a group is just some algebraic construct, just like a vector space. If I have a vector space, it's also defined in a similar way where we have two vectors and we know how to add them. So we have a vector addition, which is also a binary operator defined for it. If I take two vectors, add them together, it gives me a new vector. And so this is in a similar way we can define groups as having such a group product and an identity element and an inverse element. But so it doesn't help too much to linger on these specific definitions. Let's go over some examples. So a very basic example of a group is the translation group. And the translation group, it consists of all possible translations, which are parameterized by vectors in R2, and it is equipped with a group product and a group inverse as follows. So G represents my group elements, so two elements of this set, and I can combine it together with the group product. So if I have one translation and another translation, G prime, I can combine it together with the group product, and I do that via vector addition. So that's how I define this group product. I just add these vectors. And similarly, there's a group inverse, which is negating this vector. And you can easily show that if you apply G to its inverse, so I mean x minus x, I get the identity vector, the zero vector out of it. So we also have an identity element there. And it's often useful to think about groups as transformation groups. So a group represents a translation. So I could translate this robot to this location, I can translate it again, and then the group product tells us what if I were to, what will be the net operator of concatenating these two translations. I might as well do that at once with a translation given by the product of these two translation group elements. And you might wonder here, like, why do we need a group structure at all for the translation group? And I guess the answer for that is we don't, because these really behave as vectors. So we just add them and we subtract them, and we can do that with vectors. But we do this by this new notation, the group product. And I do that because if you now move on to a next group, the rotor translation group, we no longer can just simply add the group elements because we have a sort of mixing going on between rotations and translations. So let's go over the rotor translation group SE2, where SE comes from special Euclidean. It's the special Euclidean motion group. Okay, so the group SE2 is, it consists of a space of translation vectors and rotation angles or rotations. The notation for the rotation group is actually SO2, special orthogonal group, but I can identify it for 2D rotations also one rotation angle. So I sometimes equally write S1 or S2. But sorry for losing focus here. So the rotor translation group consists of translation vectors and rotations in SO2 and is equipped with, again, with the group product and a group inverse. So the group product again tells us how to concatenate two of such transformations. So if I have one translation and a rotation and another translation and rotation, and I apply them one after each other, this would be the netto rotor translation. So maybe best observed in this example. So we have this robot, we can rotor translate it again, and then we rotor translate it again with the G prime. And this results in one net rotor translation, right? I can also just directly rotate and translate the robot to this location. And the group action or the group that does this, the transformation that achieves this result, is described by the group product. And now we see that we cannot just simply add up these translation vectors and the rotation matrices, because that would not bring us to this desired result. And we see actually that we have this action of the rotation on the spatial part in it. So in order to describe how two such rotor translations are combined, we need a definition of a group product, because we cannot just simply add these translation and rotation matrices. For example, what does it mean to add a rotation, two rotation matrices? Are you going to do that element-wise, or are you going to do this in some other way? Okay, so that's the rotor translation group. And many groups, like all the groups considered in this lecture, have certain matrix representations. So, for example, this is a well-known way of representing rotor translations, where we have a matrix. This part takes care of the rotations, and this takes part of the translation and sort of homogeneous coordinates. If you have such a matrix representation of your group, then the group product is simply defined by a matrix multiplication. And that's what you see over here, right? If you have one matrix representation of the group, so a translation vector and a rotation, another translation and rotation, then the new rotation is achieved by r theta times r theta prime. And you can easily derive that the result is a rotation matrix with the rotation angles added up. And we see that this rotation matrix is multiplied with x prime plus x times 1, which gives us this thing. And it's the same as we saw in the parametric form. So we do not necessarily need to compute all these matrix multiplications if we know what the result will be. So we might as well work in parametric form and say that the group product is defined as such, right? This is the new translation, and the rotation is represented by this new rotation angle, modulo 2 pi, of course. Okay, now one of the reasons that we like to work with this group theoretical notation is that we do not always want to write out how these transformations explicitly. We can just reduce it to this dot operator, and that this keeps the equations often kind of clean and simple. Okay, and this is then another example of a group useful in computer vision and maybe deep learning in general, the scale translation group. So this one consists again of translation vectors in R2 and scaling vectors in R+, and it's again equipped with a group product and a group inverse as follows. So maybe the depiction here is like we can transform an object by translating it and scaling it. We can do that again with another translation and scale vector, ending up with this net result. We could also obtain this at once, this result, and then this transformation is described by the group product, the product of these two group transformations. And you see here, what does it mean? We scale the translation vector of the second one, add a shift to it, and we scale the overall scale vector with multiplication. Right? If I scale something with a factor 2 and then scale it again with a factor 2, we have a netto scaling of a factor 4. And now, okay, so this is the scale translation group. Also here we have an identity element, so no translation, a scale factor of 1 multiplied with 1 is just 1. And it has this matrix representation where here on the diagonal we have S, the scale factor, times the identity matrix. Now, what is important to note here is that these groups that I just covered, like the rotor translation group, the scale translation group, they're all examples of affine groups that consist of a translation part and a sub-transformation that acts upon the spatial part. For example, we had rotations acting on the spatial part or scaling acting on the spatial part. And so this is the type of groups that we're going to see a lot in these lectures because they have some convenient properties, namely that we can purely focus on the subgroup H part. If we know how to do the group product there, that's useful because that's all we need for that part. And if we know how the group acts on the spatial part, then these two together completely define the group product, because translation is trivial. We just add this translation vector to it. We only need to know how to transform these Euclidean vectors via these group elements in H. So, and we will see in the tutorial as well, if you want to implement group convolutions for affine groups, what we need to know is how H transforms elements of RD. So how positions or Euclidean vectors are rotated, or how they are scaled or rotated and scaled simultaneously. And then the group product is automatically defined, and we also have an inverse to it. And maybe a last note on terminology. These kind of groups are called semi-direct product groups, because we have a group of translations and we have a group of, let's say, rotations. So both are groups on their own, but once we combine them via a semi-direct product group, it means that the H part is just combined with it. It's group product defined as such, but for the RD part, the left part of this fish type symbol, there's some interaction, mingling going on between transformations in H and the translations. So that's why you call it a semi-direct product group. And you would call it a direct product group if, we wouldn't have this H over here, and we would have just translation plus translation and rotation times rotation, for example. Okay, so now back to our motivation. So I said that we're going to use group theory to sort of simulate this idea of recognition by component, this notion from psychology of vision, where we build objects out of their lower level parts by placing them into relative configurations. And that's precisely what we're going to do placed. So consider this case. So suppose we want to come up with a phase descriptor like this. So we could do this by placing a set of points into this relative configuration such that the outline of the face is clear, the eyes are clear, the nose is there, and the mouth is there. So this point cloud, it could represent a face. And now if I want to know, so each point represents actually a group element, right? So it's the identity shifted to this location, to this location. So each point could represent such a translation vector. Now, then if I want to know what this face looks like at any other point in space, for example, this element G over here, I just need to align the nose to this point and shift everything accordingly. And that's what we're going to do precisely with this group product. So we multiply every point in space with G on the left, which means we're translating the nose to this point, we're translating this red point over here by multiplying it with G over there. So if we call this point blue point G prime, then the point that we see over here is G prime with G multiply on the left, which essentially means we have X plus X prime, if we look at it in this parametric form. And I think this exposes an important aspect of group theory, which is that if we know how to describe a world locally, for example, what a face looks like at the origin, for example, we also know what it looks like at every other point in space by just moving this relative configuration of points to another point in space by the group product. Now, we can make this more interesting by now describing objects or features based on group elements in SE2. For example, again, now we're going to describe a face, but now the core features or the parts that make up this face are, for example, local orientations or line segments. So we have this contour of the face where all the lines are somewhat aligned, and we have the eyes. We have an orientation of the nose, for example, pointing to the right, and we have this mouth over here, with also composed out of local line segments. So now each part is represented by a group element, right? This blue arrow could be the origin rotated to its proper orientation and then shifted to the right location. So now we have a face described by local orientations. And now we can use the same group theory as before. If we want to know what does such a face look like at an arbitrary other position and orientation, then we simply multiply everything on the left with the group element. So I can align this nose with this group element over there by multiplying, the nose on the left with a G. And we do that for every other point. And then we see that the face is roto-translated to this new location. And again, the nice thing about group theory is if we know what this face looks like at the origin, I know what it looks like over here. And this relative configuration of points stays intact, it stays the same. So the core representation is left untouched. We just shifted the entire bunch of parts to the right location without tampering with its relative configuration. Okay, so this is all nice. So we can think of collections of group elements as describing some feature or some object made out of lower level parts. But yeah, we need to translate this somehow to CNNs. We want to use this knowledge to build group convolutional neural networks. So on the one hand side, we have that descriptors could be described as a point cloud of parts in certain poses relative to each other, for example, relative to the nose. But what we can think of a convolution kernel of as a density or a function on the group that assigns to every relative position relative to the nose a weight. That's what a convolution kernel does, right? It assigns a weight to the upper right pixel of the central pixel, to the top and left. And so these kernels describe features by assigning weights to relative locations. Okay, so we could easily do that also, of course, in this group convolutional setting. Now we just saw that a point cloud, so it's such a feature descriptor, transforms via the group product, but we also need to know how to then transform these functions. And this is going to happen via so-called group representations. Okay, so let's just give a formal definition again. A representation, rho R for representation, is a group homomorphism from G to a general linear group on this vector space V. So homomorphism means that we initially have a group over here, for example, the group of translations, and the space of invertible linear transformations that transform some vector space that also forms a group structure. And we're not going in detail there, but the essence is that we can call such a rho as a linear transformation that is parameterized by a group element G. And it transforms some vector in some vector space. It could be a space of images or actual, vectors. And it preserves the group structure. And that is what makes it a homomorphism. So I can transform my vector V. I can transform it again. So this describes one net transformation, which I could also describe via the group product. So that it's parameterized by the product of these individual transformations. So let's make it visual. So we have a vector. We can transform this vector via some representation rho, which is parameterized by a rotation angle, for example, which generates this vector. If I then rotate it again with, let's say, G prime is another rotation angle, I end up at this location. And I could have as well have done that directly with the transformation or using the representation, which was parameterized by the product of these two group elements. Okay, so representations are transformations that respect the group structure in the following way. And this essentially means that we can transfer this group structure to other type of objects. So we're not limited to apply the group product to the group elements, but now we can also stick to this group structure by letting the group transform other type of objects, such as vectors or such as images. So, and when we are transforming images, we're going to talk about what we call the left regular representation, or the regular representation denoted with this L, left regular representation parameterized by a G. So it is a representation that transforms functions by transforming their domain by the inverse group action. So we're going to think of an image as a function, f, that assigns to every point in space R2 some value. So it's a function, and if we then know how to transform the domain of this function, then we also know how to transform the function itself. And that's how regular representations are constructed. So here an example again. So this is an image, a function on R2, and we know how SE2 transforms two-dimensional vectors. So we know how to rotate and translate a two-dimensional vector. So if we apply then the inverse group action to the domain, we obtain a shifted image. For example, this smiley face can be rotated and translated by transforming its domain and then resampling, let's say. We can do that again. And this generates a net effect of rotor translating this image. And it's easy to show that such, let's say, induced regular representations from the group actions, that they satisfy the group structure in such a way that apply the representation once, and another time we could also obtain the result with the representation which is parameterized by the group product. So this is a proper representation. Okay, so this is cool. Now we can also apply the group structure to objects such as images. And now what I just showed, these representations are all instances of what you generally call a group action. So the group product is what you say is the action of the group on itself. So the group acts on another group element and that spits out a new group element. It always spits out something on the domain of the form on which it is acting. We also now know how to transform images. We do that via the left regular representation. So this representation acts, in this case the group G acts on images F via the representation on the space of images. But we also can define separately how the group acts on the space RD. And sometimes in these lectures I'm going to use this notation for it. So you see, all of these operations, they satisfy the group structure, and we might use different symbols for it. For example, the dot to denote how to concatenate two or group elements, or what to denote a group product. We can use a symbol like L or rho to represent the representation of the group, and this O dot to represent the group action on an Euclidean vector space. But since all these group actions all are linked back to this core group product, we do not necessarily need all these different notations, and sometimes we simply write G acting on G prime, or G acting on a function F, or G acting on X. But this can be confusing at times. So often it's convenient to use different symbols to denote the different forms of the actions and the objects on which they act. Okay, so now we have everything in place to give a definition of equivariance, you know, what this course is all about. So equivariance is a property of an operator. So an operator could be a neural network layer which maps an element in X, could be an image, to another element in Y, for example. So the output space could be different than the input space. So, okay, so phi is an operator, for example, a neural network layer, and the equivariance is then a property of this operator, which tells us that this operator commutes with the group action. So, okay, a group action. So we know how to transform elements in the space X. So we denote that with the representation of the group G acting on the space X. So that's why I use this label here for now, parameterized by a group element. So, for example, it could be the translation group. We know how to translate this image to this instance via the translation representation acting on images. And equivariance is such that this commutation diagram holds, right? So it doesn't matter if I first translate and then apply the convolution, or first apply the convolution and then translate it. As long as the final result is the same, then we say that the operator commutes with the group action, and thus the operator is group equivariant. Okay, so now you know everything that you need to know in order to understand group convolutional neural networks. So let's go to the next video in which we are going to use these tools to construct equivariant neural networks.